Okay, so question 7, the last one in this paper. Looks like it's a question about light and waves, properties of waves and things like that. A baby monitor has a sensor unit that transmits an image of a baby and the noises the baby makes to the monitor unit. The monitor unit then displays an image of the baby and emits the noises the baby makes. Compare the properties of the waves that transmit images and noises from the monitor unit. Right. So to be honest, I think this is needlessly confusing and a bit too much text to start us off. But basically they're saying, like, imagine you have one building and in which you have your child and there's a camera and a microphone there and it transmits a signal, and say you could be in another room and you could be watching on a monitor. There's your monitor that's also connected via, aerial. So on your monitor screen here, you could sit and watch what's going on with the baby on here. And it wants to know, how do the sound and the light go from the screen and the speakers to you? That's what they're talking about. So essentially what they're really asking you to do is compare light and sound. Light and sound. Okay. Now, light's a bit of an odd one. You'll hear people talk about light waves, and light does behave as though it's a wave, but that's really a deep physics thing. But what you're supposed to know anyway is that light is a transverse wave, and that it oscillates up and down, but when it's moving from the left to the right or from the right to the left. So its oscillations are at right angles to the direction of energy transfer, and this is the direction of energy transfer, right? But for sound waves, if we can imagine, say, a tuning fork, when you whack a tuning fork, the legs wiggle about sideways like this. They wiggle about sideways like this, right? And as they wiggle backwards and forwards, they are slapping into the air. And air, you can imagine, as being made up of lots of little particles of gas molecules flying around. And when these things move backwards and forwards and slap into them, they squish some of the molecules up all close together, leaving gaps that are less squished together, more squished together, less squished up, more squished up, right? So what we're really saying here is that as this wave travels through this medium in this direction, the particles themselves are just moving backwards and forwards in that direction. So there is a difference between longitudinal waves. This is a longitudinal, and this is a transverse, right? Transverse wave. So longitudinal waves are things like sound, and transverse waves are things like light, right? Sound moves much slower than light. Light moves much faster than sound. So you can see that when you see video footage of, say, an airplane being hit by lightning. Wait for it. See the flash, and then you hear the sound much later, and that's because the speed of light is so much faster than the speed of sound. So these are all the kind of points we need to be making. So start with bullet point number 1.
Let's just say the simple stuff. Light is much faster than sound. So light is much faster than sound. Light actually moves at 3 times 10 to the 8 meters every second. That means 3 with 8 zeros meters every second. And sound moves at about 330 meters every second. Right? Let's make another point. Light is a transverse wave that can travel. Transverse? Yeah, it's a transverse wave that. This is another amazing thing about light, is it can travel through a vacuum. Light is a transverse wave that can travel through a vacuum. So it doesn't need a medium to move through. Sound, on the other hand, is a longitudinal wave like this. Longitudinal wave. Right, so I think I've mentioned all the key points here. Sound is a longitudinal wave. I've mentioned the speed differences, I've mentioned the fact they're different types of waves. So sound is a longitudinal wave. I might just mention that, just in case I've got a bit more space, I may as well add a bit more detail. Longitudinal wave. The oscillations. Ooh, I better get the spelling correct. Bit of a tough one to spell that is. I might go for vibrations instead, easier to spell. Vibrations are in the same direction as the energy transfer. Energy transfer. Right, so what I'm saying there is that the vibrations are in the same direction as the energy transfer, whereas when it's a transverse wave, the vibrations are up and down, but the energy transfer is at right angles to that. Okay, so that's
part 1. Let's look at part 2. The sensor unit can detect infrared and visible light. Suggests one advantage of being able to detect infrared. I'll show you a funny clip here, but basically you can see in the dark. Okay, write down an equation that links frequency, wave speed and wavelength. So velocity, or V, equals frequency times wavelength. Right, sometimes you'll see this written as C equals F lambda, because the C means the speed of light. Often we're dealing with this with speed of light, but that's the formula. F is frequency in hertz. This is the length of a wave. That could be from any two identical points on a wave, but usually we just show it like this. So it could have been measured from there to there. It would have been the same length, right? So that would be the wavelength in meters. So if you know you get, say, let's just say you get, let's say that's 1 meter long, right? And you are standing here and you count, say, 3 of these waves passing you in 1 second. Right, that means 3 meters of wave has passed you in 1 second, right? And if you just say the 3 here is the frequency in hertz, right? The frequency in hertz, you're just doing 3 times the length of the wave in waves in meters, and you'll get your correct value for the speed of the wave or velocity of the wave. Right. So 3 marks now available for being able to calculate this bit. So let's take our time and do it nice and slowly. Take the formula and write it in. V equals F lambda. Sub the numbers you know in. Do I know the velocity? Oh yeah, I do know the velocity. They've given me 3 times 10 to the 8. 3 times 10 to the 8. Now you can write it in like that if you want. If you know how to do it on your calculator, it's the X button to raise the power. If you're not sure, it just simply means 3 with 8 zeros. Equals now, do I have the frequency? Oh no, I'm supposed to calculate the frequency, so that's still there. Equals F and then times lambda, which is wavelength. Do I have the wavelength? Yes, I do, and it's in meters, so I don't need to change it. 0.125. Right, so now I'm here. It's time to rearrange the equation. Now again, you can see it's multiplying here, so maybe it's pretty obvious you need to divide, but some students do find this quite tough. So if not sure, use your triangle, cover up what you're trying to find. We're trying to find F. Always on in these triangles, the bottom are the things that are multiplying each other. So F equals V over lambda. F will equal V divided by lambda. The velocity, 3 times 10 to the 8, or 3 with 8 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. So that is 3 times 10 to the 8. Divided by 0.125, 0.125, and this should give me the correct answer. I've checked that the units are all correct. It's in hertz, not kilohertz. It's in meters, not centimeters or kilometers. So I should get my correct value out. 3 times 10 to the 8 divided by 0.125, and I'm getting a very large number. So I could write this as 2, 4, 1, 2 zeros, 1, 2, 3, 1, 2, 3, right? I could write that as the answer. Or I could write 2400 megahertz. or I could just leave it as this. The safest thing to do is to just leave it as this answer. Okay, I hope you found this useful. Thanks for watching.